We're going to start chapter 8 in this video. And chapter 8 is still on alkyl halides, but this time we're specifically going to talk about elimination reactions versus substitution reactions. So elimination. At the end of this chapter, we're actually going to mix them together. So given an alkyl halide, a nucleophile / base, and a solvent, we're going to determine what type of reaction will it undergo. Will it substitute? Will it eliminate? And then just as we had two types of substitution, we are going to have two different mechanisms for elimination. So we will have 4 different mechanisms, and we'll determine which of the 4, sometimes more than one actually, will it proceed through. So first of all, we'll just talk about elimination in general, a little bit about alkenes, and then get into the specifics of the 2 types of mechanisms. So elimination reactions, this is our second common type of alkyl halide reaction. So it's really just a continuation of the last chapter. With elimination reactions, we are going to produce pi bonds. If you remember back from chapter 6, we had 4 common types of reactions. Substitution, which we did cover in chapter 7. Addition, where you're removing a pi bond. We have a pi bond and then something is adding, and the pi bond is then goes away. Elimination, where we're actually removing something from our molecule and producing a pi bond, so produces pi bonds. And then we had rearrangement reactions also in chapter 6. So this is our elimination. So just kind of a quick example. I'll put my halogen on here, and then I'm going to put a hydrogen. There are 2. I'm just going to show one of them, however, because one of them is going to get removed. I'm going to add a base to it, so B for base, and then that base is going to end up taking that proton, the electron between the proton and the carbon that it's bonded to are going to go down and make a double bond between that carbon and the carbon that's bonded to the halogen, and then that halogen is going to leave. Remember, this carbon is partial positive, right? I do have that dipole. And I'm using base, we're using Bronsted-Lowry sort of idea. Bases want to take protons, so those electrons are being given to that hydrogen. These electrons are going down, and then the electrons between that partial positive carbon and that halogen are going onto that halogen and is going to end up leaving, so it's a leaving group. This can happen all in one step, or it can happen in 2 steps. So we are going to have 2 different mechanisms, just like we did with substitution, but regardless, when we're done, we're going to end up with an alkene as our product. So substitution, again, we're breaking 1 sigma bond and forming a new sigma bond. Here we're breaking a sigma bond. Actually, we're breaking 2 sigma bonds and forming a pi bond. We're actually forming a sigma bond also between the base and the hydrogen. I guess I would just focus on the forming the pi bond part. I guess I would have a positive charge the way I started it, and then X minus floating around. Kind of a real example. Let's use a cyclic one, and I'll put a bromine on there. And then let's use KOH, right? Potassium plus hydroxide with its negative charge. The potassium we don't care about, so OH minus is my base. And we would end up with that alkene. Plus water. I don't really generally require you show these other things, but I would have water, and then I would have potassium bromide, right? K plus is still floating around, even though it's not reactive, I still have it. And then my leaving group is bromide. So because potassium is a positive charge and bromine is a negative charge, they would be hanging out with each other. It is a dehydrohalogenation reaction. I don't generally use that term, but it does come up if you're looking up other sources. The book uses it. So a dehydrohalogenation reaction is just a type of elimination. So D means we're removing, right? So we're dehydrohydrogen and then halogen. So we're removing a hydrogen and a halogen, right? We're dehydrohalogenating it. So the removal of H and X, right? It's a very common way to produce an alkene. In our alkene chapter, which I think is chapter 10, we'll actually see this reaction again as a way to produce an alkene. Common things that we're going to use as bases. Is the OH, we already did that one. But then if I was to replace that hydrogen with an R group, that's also pretty common. These would be alkoxides. So if it was 1 carbon methoxide, 2 carbons ethoxide, I'm not going to hold you to those names, but I'll probably say something like methoxide attack, so just so you know what I'm talking about. Those are going to be common. NH minus is also a really strong base. Sorry, NH2 minus. It's actually stronger than OH minus, if you know your trend on the periodic table for basicity. I'm going to add some other things as we go through, but for now, those are going to be, you know, really common. If I give you any of those, almost always it's going to eliminate. I do want to look at that carbon-carbon double bond real quick, right? So I'm just going to throw some hydrogens on here first. We haven't talked a lot about alkenes yet, so do know that those carbons are sp2 hybridized, right? Both of them. Right? They have 3 electron groups. They're planar. Right? Trigonal planar. And then that pi bond, remember, it overlaps above and below the plane of the molecule. So this, just like our cycloalkanes did, alkenes lack free rotation, right? This carbon, we could do its 3 sp2 orbitals, right? Throw some hydrogens on there. My second carbon with its 3 sp2 orbitals, my hydrogens. And then remember, my pi bonds were made of the side-by-side overlap of my p orbitals. These guys are unhybridized orbitals, the p ones. And then they're overlapping here and here. So because they're overlapping in those 2 spots, it does lack free rotation. So pi bond. So we can't rotate, cannot rotate the molecule. We should say rotate the atoms, maybe that's a better way to say it. About the pi bond. Right? Just, I want to make sure that I'm super clear on this. So if I had a single bond, right, these 2 carbons, and then let's put some R groups on them. Right, because this sigma bond is overlapping just in the one spot, end to end, we can take this, right, and I can rotate around that bond. So the original one I drew would be my staggered conformation if you were to look on the end, kind of put it in a Newman projection, but I could rotate that and then end up with this eclipsed version, right? And we said they're not stereoisomers, they're conformations, because I can produce them by just rotating that bond. So they're really the same thing, right? That bond can freely rotate. It's just that the energy of the first one is less than the energy of the second one because it doesn't have torsional strain and it has much less steric strain. If I was to look at the alkene versions of these, so less groups, right? Because it's sp2 hybridized instead of 3, but I'm still putting 2 R groups on. I'm putting them opposite. Or I can draw another one where I put them on the same side, right? So here I had them opposite, but then I rotate that bond and get them on the same side. So these are actually the same molecule, just 2 different conformations. I cannot rotate I'm going to write it on there, but then undo it because I can't do it. This is totally wrong. We can't do that. Because they're locked above and below, these two molecules are actually different. These are stereoisomers of each other. I can't get one from the other by rotating a bond. These, right, these guys are conformations. Sometimes called conformational isomers. I don't like that term because then it's confusing with conformations, or it's confusing with stereoisomers, right? Because they're not stereoisomers, they're conformational isomers, which is different. I just ran out of room, so I'm rewriting it. So sometimes called conformational isomers, but again, they're not actually isomers. Here, right, these guys, they're actually different. And we can use the same sort of terminology that we use with our alkene, with our cycloalkane, sorry. Here, my two R groups are trans to each other, right? If I was to draw a line through my double bond, they're on opposite sides. This is on the opposite side of the double bond as this one, so they're trans. On this one, they're on the same side of the double bond, so this would be considered cis, right? I don't have free rotation around that bond. I cannot freely rotate. Because of that, we get stereoisomers. So to have cis trans isomers, each of the carbons involved in the double bond need to have one, and actually only one, carbon-based group attached to them. So to have cis trans isomers, each carbon involved in the pi bond, right, the carbon-carbon double bond, must have one and only one R group, carbon-based group. Bonded to it. If it has more than one, it can still have isomers, but they're not cis trans isomers. They're a different type of isomer that we'll talk about in chapter 10. For now, we're just going to stick with the cis trans. That says them. Sorry. Let's fix it. Bonded to, that's not a lot better. Bonded to them. So it's just an example. If I was to do this, I'm going to make both of these hydrogen, and then this is a hydrogen. I'm not going to have stereoisomers on this one. No stereoisomers. Right, I only have one R group right here, right, one carbon-based group, and there's nothing to be cis or trans to it, right? There's nothing on the same side or the other side. Hydrogens, I mean, well, there's something, I'm counting them as nothing, so there's no carbon-based groups. If I was to have those R groups on the same carbon, right? When I'm talking about cis trans, I'm talking about looking across the double bond, right? Whoa. Let's just start that one over again here. Sorry. Okay. So double bond. If I put them on the same carbon, right, when I'm doing cis trans, what I'm doing is I'm looking down, right, I'm like basically drawing a line where this double bond is, and I'm looking to say, are those two groups opposite of each other or on the same side? And these guys are on the same carbon. So I'm not going to have cis trans stereoisomers for this one, right? If I was to draw it where I had them on the carbon where the two hydrogens are, it's the same thing, just flipped over. So something like this, where they're on the same carbon, right? They're attached to the same carbon here, right? They're both attached to this carbon. I'm not going to have stereoisomers either. Right, to have them I'll put a hydrogen here, my R group, hydrogen, and an R group. If I draw this dotted line, right, these guys are attached to different carbons. They're on the same side of that, so this one is going to be cis. If I was to draw it again, they're attached to different carbons, right? And when I draw a line through that pi bond, they're on different sides, so that is going to be trans. If I go back up to this first one, I guess it's the second one, but this one, they're on the same carbon, no cis trans isomers. I'm going to draw one more for you here. And this time I'm going to put 3 carbon-based groups. This would be considered tri-substituted. I'll review that here in a minute. Don't forget the pi bond. So these would have cis trans isomers, assuming that the 2 R groups on that first carbon are different. So I've just added a little prime to show that that's different. Let's color code them. So let's make this one orange, and we'll make this red and purple. So the orange R group and the purple R group are trans to each other, but the red R group and the purple R group are cis to each other. So these do have stereoisomers, but they're just not cis trans stereoisomers. We would have to use a different naming system. So these have stereoisomers, but not cis trans. They're actually easy isomers, and we'll talk about those in chapter 10. So just know for now, to have cis trans, I have to have 1 R group attached to each of the carbons in the double bond, and only 1. As soon as I get more than 1, while stereoisomers are possible, they wouldn't be called cis trans stereoisomers. We have to use a different naming system. If the 2 R groups are on the same carbon, no stereoisomers. And if I only have 1 R group, no stereoisomers. I do want to talk about substitution real quick. I've thrown a couple of those terms out already. So substitution. So we can have mono-substituted. Right, if it's mono-substituted, it's only going to have 1 carbon-based group attached to the carbons in my double bond. So my double bond, and I'm going to have 1 carbon group. Doesn't matter which carbon I attach it to, but I'm going to have 1 R group. Di-substituted, we can actually get di-substituted 3 different ways. It's going to have 2 carbon-based groups, but I can put them on the same carbon, right? This is our one where we wouldn't have cis trans isomers. I can draw my cis conformation where they're on the same side. They can both be going up or they can both be going down, but they're going on the same side. So my 2 R groups on the same side, and the second one's my cis. And then we could draw it where those 2 R groups are on opposite sides of that pi bond. And that would be my trans version. All 3 of these are di-substituted, right? All 3 of them have 2 R groups attached to the carbons involved in the pi bond, but they're different. In general, the trans is going to be more stable than cis because I have less steric strain. Right, the other two, those R groups, are much closer to each other and they have more steric strain, so less steric strain. So that's going to make my trans stereoisomer more stable than my cis. Tri-substituted, just as it sounds, it's going to have 3 R groups attached to the carbons involved in that double bond. And then tetra-substituted, tetra is going to be 4. So tetra-substituted. So mono, 1 R group, right? Attached to the carbons involved in the pi bond, di, 2. Different ways we can achieve that, but still 2. Tri-substituted, 3 R groups. And then tetra, 4. In general, the stability of our alkene is going to increase as its substitution increases. So in general, alkene stability increases with substitution. And then if you're comparing a di-substituted to another di-substituted, the trans version is going to be the more stable. So a quick example for us. I'm going to give us some pairs of alkenes, and we want to determine which in each pair is more stable. And then that one or this one. So the first one or the second one, which one is more stable? So hopefully you guys are thinking this one. So more R groups, it's going to be more stable. This one or this one. So I hope you're thinking this one. That one is our trans version. Steric strain, not us. And then how about, what should we do? How about those two? So I hope you're thinking the first one. The first one is tri-substituted, right? This carbon right here is attached to this carbon and this carbon, so that's 2 carbons. And then this carbon is attached to this one, so this is tri-substituted. Where this one is only, my second one, sorry, this one is only di. So the 2 carbons by double bond, they're attached to this carbon and this carbon, so 2 of them, di-substituted. Again, the more substituted alkene is going to be our more stable alkene.